Is the audio clear? Yeah, I guess so. Okay, so welcome to the Smart Crack series for NEET 2022, and today we are going to cover gravitation in one shot. So let's begin. So gravitation starts with Kepler's laws of motion. So what are Kepler's laws of motion? So these are laws for motion of a planet around the sun. Okay, yeah, good morning Sugandhan. So these are laws for motion of planet around sun. Okay, so they say that there is first law, which is law of orbits. All planets move in elliptical orbits with sun at one of the focus. Okay, so we know that there are two foci to an ellipse. So if we consider an ellipse like this, then there will be two foci and sun is at one of the focus. So let's suppose sun is here. Okay, so this is our planet. So sun, this is sun and this is some planet. So every planet revolves around the sun in an elliptical orbit with sun at one of the focus of that ellipse. Okay, then next law is law of areas. So law of areas says that if you join a line segment from position of sun or center of sun to the center of planet, then that line segment will sweep out equal areas in equal intervals of time. So let's suppose this planet goes from this position to this position in some time, let's call it t. Okay, so area swept out will be how much? So this much will be the area. Okay, I will mark it. So this much is the area swept in time t, and then suppose it goes from this position to this position in the same time. Okay, same amount of time, then in this case there will be some area swept. Okay, so area swept is suppose this much. Let's call this area A1. This is not visible, I guess. Okay, let's call this area A1 and this area is A2. So time taken to go from, let's say, A to B is equal to time taken to go from C to D. Then this area A1, the area A1 will be equal to the area A2. Alright, so this is Kepler's second law. It is law of orbits. So what is law of orbits? So if you join a line from center of the sun to center of planet, then it sweeps out. It moves through equal areas in equal intervals of time. This is the second law. Okay, and then there is third law, which is law of periods. So what is law of periods? The square of period of a planet is proportional to cube of semi-major axis. Okay, so we know that there are two axes to an ellipse. So this one is known as, let's change the color. So this one was still. So this one is known as major axis. So if you take half of that, you will get semi-major axis. Okay, so law of period says that t square, if t is the time period of revolution of this planet around sun, then square of that time period is directly proportional to r raised to 3. And what is r? It is half of this axis. Okay, the major axis. Okay, the bigger axis. All right. Okay, so these are Kepler's three laws of motion. Kepler's three laws for planetary motion. Okay, so let's move ahead. I guess there should be no question in this. Then we come at Newton's universal law of gravitation. So what is Newton's law? Every object of the universe attracts every other object of the universe with a force which is directly proportional to product of their masses, and it is inversely proportional to the square of distance between them. Okay, so let's suppose we have two masses, two objects of masses m1 and m2, then they will attract each other and there is force due to gravity between them. Okay, so there is gravitational force of attraction. It is equal to what? G times m1 m2 upon r square. Okay, so this G is known as the universal gravitational constant. Okay, and what is value of G? It is given most of the times in exams. So it is 6.67 into 10 raised to minus 11. And what is the unit? So if you take this r square on this side and m1 m2 also on that side, so it will be force multiplied by distance square divided by square of mass. Okay, so you can find G from here. It will be what? F suffix G, which is gravitational force, into r square divided by m1 m2. So unit of force is Newton, unit of r is what? Meters. So we have r square, therefore it is meter square, and in denominator we have square of mass. Okay, mass times mass, so unit of that is kg, so we have kg square in denominator. So this is the unit of universal gravitational constant. Okay, after that let's move on. So next topic is acceleration due to gravity. Okay, so what is acceleration due to gravity? So it is the acceleration with which objects fall freely towards the center of the earth. Okay, so if you release some object, it will fall with some acceleration, and that acceleration we call it as acceleration due to gravity. Okay, so now let's suppose that this is our earth. Okay, and then you take some object over here. So this is the object. So what is the force acting on this object? It is the gravitational force. Okay, or you can say it is the weight of this object. What is weight of the object? It is the gravitational force exerted by earth on that object. So W equals to mg is the weight, and so gravitational force we know it is what? Gmm or r square. Okay, it is Gmm divided by r square, and it should be equal to the weight, because weight is nothing but what? The gravitational force exerted by earth on the object. Okay, so this m and m will get cancelled out, and you will get G equals to what? Gm over r squared. Okay, so if object is on surface of earth, it will be Gm over this capital R square, where capital R is what? It is radius of the earth. Okay, if it is at some distance h, then for G at some height h above the earth's surface, it will be what? Gm over r plus h square, because distance of that object from the center of the earth will be how much? It will be r plus that height h. Okay, so this is the formula for acceleration due to gravity. On earth's surface we have this formula, G equals to Gm over r square, and at some height h the formula changes to what? G at height h is equal to Gm divided by r plus h square. Okay, it's simple. After that, let's see what is variation in acceleration due to gravity due to the height, due to the depth, due to rotation of earth, etc, etc. Okay, so let's see variation in G due to the height. So G at height h is equal to, it is given by G multiplied by 1 plus h upon r raised to minus 2. Okay, this is the formula. And how do you get that? So if you divide this equation of GH by this equation of G, you will get GH divided by G, and then you take g on the other side and you do some calculations, and then you will get relation between gh, the acceleration due to gravity at height h, and g. Okay, so what's that relation? So variation in g due to the height, it is given by this formula. Gh is equal to g multiplied by 1 plus h upon r raised to minus 2. Okay, and if h is very small, okay, if h is very small compared to r, then you do binomial expansion of this and you derive this formula, okay, this relation. So this is valid when h is very small compared to r. So what do you mean by very small? It can be 5% or something, okay, let's say up to 5%, 8%, at max 10%. 10% is also a big value, okay. But if h is, let's say if r is 100, then if h is up to 5 or something, then this formula will be valid, okay. If h extends beyond that, okay, more than let's say 5% value, then this formula will become less and less accurate, okay. After that, variation, next is variation in g due to the depth, okay. So this was variation in g due to height. Now let's suppose an object goes inside Earth. This is Earth. So what will happen to the acceleration due to gravity at depth d? This is the depth d at this point, let's say. What will be the magnitude of acceleration due to gravity? It is given by this formula, okay. So if you draw a sphere over here like this, okay, at depth d, then at each and every point of that sphere, the acceleration due to gravity is given by this formula. It is g at depth d equals to g, the acceleration due to gravity on Earth's surface, multiplied by 1 minus d upon r, okay, where d is the depth and r is radius of Earth, okay. After that, now we know these two formulae, the acceleration due to gravity at height h and acceleration due to gravity at depth d. We know this formulae. So what we can do is we can plot the g versus r curve, okay. G is the acceleration due to gravity, so we'll plot g versus r from the center of Earth, okay. So if you do that, what will you get? So if you see at this formula, g equals to what? G at depth d is 1 minus d by r, okay. So if d is equal to 0, what will happen? Sorry, if d is equal to r, where will you reach? You will reach to the center of Earth, okay. So the acceleration due to gravity, it keeps on changing like this. If you plot this graph, it becomes 0 on the Earth's surface. So this is g versus r curve, and it goes on increasing. It goes on increasing as you go away from center, okay. It keeps on increasing till some distance. How much distance? Till it reaches the Earth's surface, okay. So the acceleration due to gravity keeps on increasing and its maximum value is on Earth's surface. It is equal to what? we know it is gm over r square, and then it falls off. Okay, then it falls off given by this formula. It is acceleration due to gravity at height h. It is what? Gm divided by r plus h square, or you can say gm divided by r plus h is the distance of object from center of earth. So gm divided by distance square. Okay, so it falls as 1 over r square. So the curve will be like this. All right. So for r less than capital R, you have to consider this formula, and this is equation of a line. Okay, 1 minus d by r, it is equation of a line. All right. So it keeps on increasing linearly till it reaches its maximum value on Earth's surface, and after that it keeps on falling as 1 by r square. Okay, so this is how the graph of g versus r looks like. Okay, we have to remember this. All right, let's move on to the next thing. So variation in g due to rotation of the earth. Okay, so again let's consider our earth. All right, so let's consider earth. I'll draw it here. So as earth rotates, what happens? Is Suji Venkatesan sir, height is less than r means which r? Height is less than small r. See, Earth's radius is denoted by capital R. Okay, and if you consider, let's say, whatever you throw, let's say, from Earth's surface, okay, it will reach to some height. How much height? 1 meters, 2 meters, 5 meters, etc. Right? So the radius of Earth is 6,400 kilometers. Okay, radius of Earth is 6,400 kilometers. So let's say up to 32 kilometers or something. H is very small compared to R. Okay. So radius of Earth is equal to 6,400 kilometers. Okay. So now what is very small compared to this? Yeah. So it will be some 32 kilometers up to 60 kilometers, you can say at max 100 kilometers. It's very small, very, very small. And then we can use this formula. Okay. All right. Then let's see this thing. The variation in G due to rotation of the Earth. So as Earth rotates, what happens? Every object on Earth performs circular motion, right? So we know Earth rotates about this axis, which passes through its north and south poles. So as Earth rotates, every object on Earth performs which motion? It performs circular motion. So let's suppose this is an object over here at some latitude. Okay, this is the latitude. So we'll have equatorial plane, and the angle made by the position vector of that object with respect to the center, it is known as the latitude. This is latitude. Okay, this angle is suppose theta. Then the acceleration due to gravity, okay, at latitude theta, so at an angle theta, is given by this formula. Okay, yeah, welcome. So G at theta is equal to G minus R omega square cos square theta. What is omega? It is the rotational speed of Earth. Okay, the angular velocity with which Earth rotates about north and south poles. Okay, about an axis passing through north and south poles. Then g at the latitude theta, it is given by this formula, g minus r omega square cos square theta. Okay, we have to memorize it, and we are not going to derive anything over here. Okay, or very few things will derive. All right, so we have to memorize this formula. After that, then next is effect of shape of the Earth. Okay, so Earth is not uniform. It's not like a sphere with fixed radius. Okay, the shape of Earth is somewhat elliptical. So how is the shape of Earth? Shape of Earth is something like this. It is bulged at the equator, and it is flattened, somewhat flattened at what? Poles. Okay, so from this what we can say is the acceleration due to gravity must be small on equator, and it will have greater value on poles. Why? Because if you think about radius of Earth, okay, so radius is least over here, it is minimum at poles, and it is maximum along equator. If you move on any point on the equator, the radius of Earth will be maximum. Why? Because Earth is bulged like that. Okay, so this is our maximum. Okay, and we know that acceleration due to gravity, it is inversely proportional to r square. Okay, it is gm over r square, but r itself is changing. So if r increases, what will happen? Acceleration due to gravity will decrease, and if r decreases, acceleration due to gravity will increase. So that's why acceleration due to gravity has its maximum value on the poles and minimum value on the equator. Okay, it's simple. So then let's move on to the next thing. Next thing is gravitational potential energy. So what is gravitational potential energy? So let's suppose we have Earth. Okay, this is our Earth, and we bring some object from infinity. Okay, what is infinity? Where Earth's gravitational field will not be there. Okay, or it will be very negligible. Such a distance, we'll call it infinity. So we bring some object from the infinity and we put it, let's say, at distance r away from the center of Earth. Okay, so we have brought this object from very far, let's say from this point at infinity. So we have to do some work in bringing this object against gravity. So this work, okay, it is stored as the potential energy of the object. All right, so what is potential energy? It is the work done in bringing an object or a body from infinity to a point. Okay, so let's suppose we keep that object at distance r from the Earth's surface. So against the gravitational force, the work that we do, it is known as the potential energy. It gets stored as the potential energy of the object. Okay, so formula for potential energy is minus of gmm over r. All right, simple. Then I will define one more thing. So I will define a thing related to this, and it is known as the gravitational potential. This was gravitational potential energy. I will define gravitational potential. Okay, so what is gravitational potential energy? It is work done to bring an object from infinity to a point, okay, in against the gravity. So what is gravitational potential? It is work done per unit mass, we'll denote it by V, to bring an object from infinity to distance r. Okay, so it is it going outside? No, it is work done per unit mass to bring an object from infinity to a point, okay, in a gravitational field. All right, and remember, this is work done against the gravity, okay, not work done by the gravity. All right, so we have seen gravitational potential energy and gravitational potential. After that, next term is escape velocity. So what is escape velocity? So the velocity, so let's suppose we have some object on Earth, so the velocity which should be given to that object so that it escapes out of Earth's gravitational influence is known as the escape velocity. Okay, so it is bound with Earth with some energy, so we provide equal energy. So it is bound with Earth, that means its energy will be negative, so we provide some positive energy to it, okay, in terms of the kinetic energy. So we give it some velocity and it escapes out of the Earth's gravitational influence. Okay, so the velocity that should be given to it, it is known as escape velocity. So the minimum velocity with which a body must be projected to overcome Earth's gravitational pull is escape velocity. Its formula is given by square root of 2 gm over r. Okay, it is given by square root of 2 gm over r, and we need to remember a trick in order to solve problems related to gravity, and that trick is, see, g is equal to what? Gm over r square, and acceleration due to gravity at height h is equal to what? Gm upon small r square, right? So this is a trick that we need to remember. So we'll take r square on other side, so we can write Gm as equal to gr square, right? If I take r square on the other side, and if I take this small r square on other side, I will get what? Gm equals to gh into small r square. What is small r? It is r plus h, capital R plus h. Okay, so we need to remember this. Gm equals to g into r square or gh into r plus h square. Okay, so it will come in handy. So if we substitute that, what will happen? So we got this formula for the escape velocity. It is square root of 2 gm over r, and it is also equal to square root of 2 gr. So if we substitute gm equals to gr square, one of the r will get cancelled with this one and we'll get square root of 2 gr. Alright, simple. So for Earth, this value of the escape velocity, okay, good. So for Earth, the value of escape velocity is 11.2 kilometers per second. It's huge. So in order to make a body escape from Earth's gravitational bound, with how much velocity we have to throw that body with this much velocity, 11.2 kilometers per second. Okay, so this is escape velocity, and this is a trick, an important trick to be memorized in order to solve problems in gravitation. Okay, we'll see this. This trick will come in handy. After that, let's move on to the next topic. Next topic is critical velocity. Okay, what is escape velocity? The velocity with which we throw an object so that it escapes out. Okay, and the critical velocity is the velocity given to a satellite or any body which will make it revolve in a circular orbit or an elliptical orbit around Earth. Okay, so let's suppose again that this is our Earth and okay, so this is the Earth and we have this planet, sorry, this satellite, it revolves around Earth. Okay, so it revolves and its distance is suppose r plus h, where capital R is radius of Earth, capital R is the radius, h is its height. So what should be the velocity given to it, or here the tangential velocity at this point, so that it keeps on revolving, okay, in a circular orbit around Earth. So that velocity is known as critical velocity, or it is also called as orbital velocity. Okay, so what is formula for critical velocity or orbital velocity? It is square root of gm over r, gm over small r. What is small r? Small r is equal to capital R plus h. And as I told before, if we use this trick, we'll get this another formula for the critical velocity. So what do we have to substitute? The gm is equal to gh multiplied by r square. Okay, so if we substitute that, one of the r will get cancelled out with this r in denominator and we will get this another formula. Okay, so this is simple. Then if h is very small compared to r, let's say about 100 kilometers or something. Okay, so if a satellite is revolving from that height, then we can neglect the height and we can just write vc equals to square root of gm divided by capital R. Okay, we can neglect this h. Okay, and we can substitute r is equal to capital R. All right, so it will change our formula to gm over capital R, or and also g times capital R. Okay, so this is the critical velocity. And what is the relation between critical velocity and escape velocity? So we have this formula for escape velocity. Okay, from Earth surface it is square root of 2 gm over r. At some height it will be what? Square root of 2 gm divided by r plus h. Okay, so what is relation between the escape velocity and critical velocity? So I can say that escape velocity is equal to, at any height, it is equal to square root of 2 times of the critical velocity. Okay, because for escape velocity we have square root of 2 times gm over r, and what is critical velocity? It is square root of gm over r. Okay, so this is the relation between escape velocity and the critical velocity. It's simple. After that, next thing is the time period of a satellite. Okay, so if satellite revolves around Earth in, let's say, circular orbit, so we actually approximate the elliptical orbit of a satellite to a circular orbit. So what will be its time period? So time period is given by this formula. It is 2 pi square root of r cube upon gm, where small r is equal to what? It is r plus h, capital R plus h, and what is m? It is mass of the Earth, not mass of satellite. Okay, what is capital M? It is mass of Earth. Okay, then if we square this, so on left hand side we will have t square, on right hand side the square root, it will be removed and we will have r raised to 3. So from this we get t square is proportional to r raised to 3. Okay, and if you remember, this is Kepler's third law. Alright, so Kepler had stated it and we can derive it in this way. Okay, so Kepler had stated it from the data. They had observed, Tycho Brahe and Kepler, they had observed the motion of planets. Okay, and they had pointed out, they had made explicit graphs for motion of planets, and from that data they had derived the relation t square is proportional to r raised to 3. All right, so it was for planets, and you can see it is applicable for satellites also. So as the time period of planet around sun is directly proportional to t square, is directly proportional to r raised to 3. Here its time period of a satellite is suppose t, then t square is proportional to r raised to 3. Okay, so it is simple. After that, what is energy of an orbiting satellite? So we know that the potential energy is given by this formula. It is minus of gmm or small r. Then the kinetic energy, if we substitute for, we know the formula for kinetic energy, K is equal to what? Half of m into v square. So for a satellite which revolves around Earth, this velocity will be what? Critical velocity, which is square root of gm over r. So if we substitute that, what will we get is the kinetic energy of the satellite is given by this formula. K is equal to g capital M into small m divided by 2r. Okay, so if we substitute critical velocity in place of the velocity in formula for kinetic energy, because velocity of a revolving satellite is equal to what? Critical velocity. Okay, then we will get kinetic energy equals to gmm divided by 2r. Okay, and then what will be total energy? So total energy is sum of potential energy and kinetic energy. So it is given by minus of gmm over 2r. So as you can see here, this is minus 1 gmm over r, and kinetic energy is half gmm over r. Okay, so minus 1 gmm over r plus half gmm over r. You can take gmm over r common, you will get what? Minus 1 plus half, which is minus half. So it is minus half of gmm over r is the total energy. Okay, and then this is the total energy of a satellite which revolves around Earth with critical velocity. So what is binding energy? So binding energy of a satellite is the minimum energy required for a satellite to make it free from Earth's gravity. Okay, what should be the minimum energy? So for revolving satellite, the binding energy is negative of total energy, because total energy is the energy with which it is bound. Okay, it's negative, and what does the negative sign indicate? That energy with which it is bound to the Earth's gravitational field. In order to make it free, we have to provide positive energy, which is equal to what? Its energy with which it is bound with the Earth's gravitational field. Okay, so the binding energy is energy required for a satellite to become free from Earth's gravitational influence, and it is negative of total energy, so it is plus half gmm over 2r. Okay, so this is simple. All right, and this is the theory that we need to remember. It's not much. Okay, so this is the theory we need to remember in order to be able to solve problems based upon gravitation. So let's move on to the problems. Let us see first problem. The kinetic energies of a planet in an elliptical orbit around Sun at positions A, B, C are K, KB and Kc respectively. So this is a planet revolving around the Earth, and its kinetic energies at point A, B and C are Ka, Kb, Kc respectively. AC is the major axis, this is the major axis, and SB is the minor axis. Okay, perpendicular to AC at position of Sun. Okay, this is just definition. Then which of this is true? So clearly we know that object is the planet is closer to the sun, faster it moves. Okay, so if it is away from sun, its velocity will be lesser, and if it is closer to sun, its velocity will be more. Because if you take, let's say, this formula also, if you approximate it, and I mean motion of planet will be elliptical, but if you approximate it to a circle, okay, at a particular point, let's just consider the distance, then what do you get? V is equal to square root of gm over r. So as r increases, v decreases, as r decreases, v increases. So at this point, r is maximum, okay, distance between sun and the planet is maximum, and therefore kinetic energy will be minimum, because as r increases, v decreases. Okay, so kinetic energy will be minimum at point C, then it will be slightly greater at point B, and it will be maximum at point A. So let's see which of these options matches with this conclusion. So kinetic energy at A is less than kinetic energy at B, and it is less than C. This is exactly opposite, right? So kinetic energy at A is greater than kinetic energy at B, and it is greater than kinetic energy at C. That means kinetic energy at C is minimum. So this option matches, okay, our conclusion. So this is the correct option. Simple. Got it? Yes? This is simple, right? Okay. Then let's move on to the next problem. Next problem is a planet moving along an elliptical orbit is closest to sun at distance r1 and farthest away at distance r2. If v1 and v2 are the linear velocities at these points respectively, then v1 by v2 is, okay. So if you consider Kepler's second law, so what is Kepler's second law? It is law of areas, right? So law of areas, okay, this thing I missed. So law of areas is also called as law of conservation of angular momentum. Okay, or law of areas can be derived from law of conservation of angular momentum. So since there is no external force acting on this system, we consider that there is no external force, okay. So the angular momentum of a planet revolving around sun remains constant, okay. And what is formula for angular momentum? Angular momentum, it is r into p. I will just take magnitude. What is p? It is linear momentum. So r into mv, or you can say mvr, is the angular momentum. So as this planet moves around sun, r will increase, r will decrease, okay, but this quantity remains constant. Which quantity? The angular momentum, okay. So mass is anyway constant. That means what remains constant? The product of v and r remains constant, okay. So if r1 and r2 are two distances and v1 and v2 are the respective velocities at those two distances, then we can write v1 r1 equals to v2 r2, and we want v1 divided by v2. So let's take v2 on this side and r1 on other side. So v1 upon v2 will be equal to what? r2 divided by r1, okay. So which option is correct? r2 divided by r1. Option B is correct, right? Okay, I guess you can, questions are cropped a little bit. I will just balance it. Okay, give me 1 second. I will just, I guess this thing is better. Yeah, okay, I'm sorry. Did it block the theory? So did it block the part of screen where I was writing? No, na? Okay, let's move on to the next problem. Next problem is, the figure shows elliptical orbit of a planet M about the sun. Okay, this is some planet moving around sun. The shaded area SCD is twice the shaded area SAB. Where is S? This is SCD. This is twice the area SAB. Okay, this is given. Okay, this area is twice. Okay, no colors are visible on black. Anyway, this area, it is twice this area. Okay, this is given. So if T1 is the time for planet to move from C to D, okay, it takes some time to move from C to D, and T2 is the time to move from A to B. Okay, then what will be relation? Okay, so from law of areas we can say that the planet cover equal areas in equal intervals of time. That means if area is double, the time taken will be also double. Okay, so it takes T1 time to go from here to here, so area swept is double to that of this one. That means time taken to move from C to D should be double. Okay, 2 times the time taken to move from A to B. Okay, so which of this is correct? Option B is the correct answer. Okay, it's very simple. Okay, I guess this is the simplest question. All right, so let's move on to the next question. What is next question? 2 astronauts are floating in gravitational free space after having lost contact with their spaceship. Okay, there are 2 astronauts and they have lost contact with their spaceship and they are floating in the gravitational free space, gravitation free space. Okay, there is no gravitation. So what will happen? The 2 will move towards each other, move away from each other, will become stationary, keep floating at the same distance between them. So can you answer this, anyone? Yes, this is very simple. Can anybody answer this? Okay, there are 2 astronauts. Okay, they have lost contact with their spaceship and there is no gravitation. Okay, gravitation free space. What will happen? Will they move towards each other or move away from each other? There is no gravitation means there is no other object which is exerting gravitational force, but those 2 are there. Okay, so the 2 astronauts, this one, this guy and this guy, they will exert gravitational force on each other, so they will pull on each other, so distance between them will decrease, right? So they will move towards each other. This is the answer. It's very simple. Okay, so there is no other object which is exerting gravitational force, but those 2 are there, astronauts A and B are there, which are pulling on each other, they are attracting each other, so distance between them will decrease. Okay, it's very simple. So let's move on to the next problem. Any question? Okay, let's see next problem. If the mass of sun were 10 times smaller and the universal gravitational constant were 10 times larger in magnitude, which of the following is not correct? This is the question. Mass of sun is 10 times, it becomes 10 times smaller. So we'll write it like this: m prime is equal to suppose m divided by 10. It becomes 10 times smaller. Then universal gravitational constant becomes 10 times larger. G prime equals to what? 10 times of g. Okay, this is given to us. and they are asking which of the following is not correct. Okay, so let's check the options. Raindrops will fall faster. Okay, walking on ground would become more difficult. Okay, time period of a simple pendulum on earth would decrease and g on earth will not change. All right, so mass of sun is changing, and all these options, they are related to earth only, right? In none of the options sun is there. Okay, so first option, let's consider them one by one. So raindrops will fall faster. So will it happen? So see, this has nothing to do with the options. Okay, so we can neglect this because it's related to sun, not related to earth. So these things, other options, all options, they are related to this thing. So if universal gravitational constant increases, what will happen? So g dash, acceleration due to gravity, will also change. So it is g dash into m, here m suffix e over r square we can write. Okay, and what is g prime or g dash? It is 10 times g. So this will become 10 times the value of acceleration due to gravity, right? Because g is changing to 10 times g. Okay, so it's obvious that raindrops will fall faster. Okay, because now earth is attracting those raindrops with a force which is 10 times as much, okay, compared to the previous case. Previous means general case. All right, so because acceleration due to gravity has become 10 times, so raindrops will fall faster, acceleration will increase. This is correct. We want to find which is not correct. Walking on ground would become more difficult. It will become more difficult because we walk against the gravity. Okay, when we walk, when we lift our legs, we have to exert some force against the gravity, right? So walking on ground will become more difficult. Then time period of pendulum on earth would decrease. So time period of pendulum is given by this formula, t equals to 2 pi square root of L upon g. So if g increases, if g goes up, because t is inversely proportional to square root of g, then t will go down, and it is true. So time period of simple pendulum on earth would decrease. So this is also correct. So last one should be the answer, but let's check what is the last option. So g on the earth will not change. G on earth will change, and this option is saying it will not change. Okay, so this should be the answer because we want to find which of the following is not correct. Okay, so as we see, g is changing, g is increasing if universal gravitational constant increases. So this is the answer. All right, it's lengthy, but it's very simple. Got it? All right, let's move on to the next problem. The next problem is a spherical planet has mass m suffix p and diameter d suffix p. A particle of mass m falling freely near the surface of this planet will experience an acceleration due to gravity equal to. Okay, so mass is given, diameter is given, and acceleration due to gravity is asked. So this should be simple. We know acceleration due to gravity is given by what? G equals to gm over r square, capital G into m over r square. So G is the universal gravitational constant. It doesn't change unless it is given in some problem. Okay, so G is always constant. Then it will be mass of the planet divided by radius of the planet square. But all options are given in terms of the diameter, not radius. So radius is equal to what? Diameter divided by 2, because diameter is 2 times of radius. So we can write this as gm of planet P divided by radius is diameter over 2 and we have square of that. So we have 2 square in denominator of denominator, so it will go into numerator. Okay, so that gives us GP is equal to 2 square is 4 times MP, 4 times G into MP over diameter of planet square. So which of this is correct answer? Not this one, this one. Okay, option A is the correct answer. All right, so this is also very simple, very simple. Let's move on to next one. Imagine a new planet having the same density as that of Earth, but it is 3 times bigger than the Earth in size. Okay, it has same density, but it is 3 times bigger. If acceleration due to gravity on the surface of Earth is g and that on the surface of this new planet is g prime, then so we have to find out the acceleration due to gravity in terms of density. Okay, and we can do that. So we have this formula, g is equal to gm over r square, and here we can substitute what? Mass of Earth. We can write it is density multiplied by volume. Okay, so it is density multiplied by 4 by 3 pi into r cube. Let's substitute that. So what do we get? So we get g into g or r square multiplied by this mass, which is given by this formula. So rho into 4 by 3 pi r cube, and there will be some cancellation. So this r square gets cancelled with this cube, I mean r cube upon r square gives us r. Okay, so we give which gives us this formula for acceleration due to gravity, which gives us this formula, g is equal to what? G is equal to 4 by 3 pi into r into rho into capital G, pi r rho into capital G. And now here what's given? The density is same. Okay, so rho is same, density is same, but the planet is 3 times bigger than that of Earth. So planet is 3 times bigger than that of Earth in size. So what will be the acceleration due to gravity on that planet? Okay, so only r is different, because in this formula there is r density and capital G, so capital G is constant. Okay, so we can write g prime equals to 4 by 3 pi into r prime into rho g, and what's different over here? R prime, how much is that? It is 3 times r. Okay, so that's why this is equal to what? 3 times of g, because r prime is 3 times r. Okay, so option D is the answer. Got it? Simple. Yes, no? And if we, okay, very good. So if we memorize this formula also, okay, g equals to 4 by 3 pi r rho g. Okay, it is acceleration due to gravity from Earth center to the radius of Earth. This formula is applicable. Okay, because it is in terms of density. So this formula is applicable from Earth center to up to the radius of Earth. Okay, what I mean when I say this formula is applicable, I mean not like this. So what will happen? So g will become g at r is equal to 4 by 3 pi r rho g. This formula is applicable from where to where? From this point, center of Earth, to up to the radius of Earth. Okay, all right. So yes, this is also simple. This problem was simple. Then, okay, please memorize this formula also, because if we know this formula, then this kind of question can be directly solved and we need not substitute anything. Okay, so this one more formula, please add it to the formula list for this chapter. Okay, then let's move on to the next problem. So a body weighs 72 Newton on surface of Earth. Okay, yeah, my pace football. All right, good. So what is gravitational force on it at height equal to half of the radius of Earth? So its weight is given 72 newtons on Earth's surface. What is weight? It is the gravitational force. Okay, what is the gravitational force on it at height equal to half of the radius of Earth? This is the question. So this is a straightforward question. We know this formula, GH is equal to what? G divided by R plus H square. Okay, oh, I'm sorry, G to 1 minus H by R raised to minus 2, or we can take that in denominator. Okay, so we want what? The force, the gravitational force. So gravitational force or weight will be equal to what? M times G, right? So here we can multiply both equations with M. So we get weight at height H. Okay, weight at height H is given by M into GH. It is equal to M into G multiplied by 1 minus H by R raised to minus 2. And how much is H? Height is equal to half of the radius of Earth. So in place of H, I will substitute R divided by 2. Okay, so it is mg. Value of mg is given. How much is it? 72 newtons. Okay, so 72 multiplied by 1 minus R by 2. This is value of H into R raised to minus 2. Okay, and R gets cancelled out. So it is 1 minus 1 by 2, which is 1 by 2 raised to minus 2, or we can say it is equal to what? W at height H 72 into its 1 by 2 raised to minus 2, or you can take it in denominator. So it is 1 by 2 raised to 2. Okay, in numerator it is 1 by 2 raised to minus 2. So in denominator it will be what? 1 by 2 raised to 2. And this 2 is in denominator of denominator. 2 square is in denominator of denominator. So what will happen? Oh, what did I do? I have done some mistake in the calculation, I guess. Oh, it is okay. Let us check the formula. It is, I guess, 1 minus H by R raised to minus 2. It's correct only. Let us check. One plus H by R. Oh. Oh, my mistake. I am sorry. Here H is less than R or greater than R. H is less than R. Okay, I missed this thing. It should be 1 plus H by R. That's what. So it will be 1 plus half raised to minus 2. Okay, that is 1 plus half is 3 by 2 raised to minus 2 we have. We take it in denominator. So what do we get? We get 3 by 2 square, then 2 square goes in numerator. So 2 square is 4. We have 4 times 72 divided by 9. Okay, so sometimes those mistakes of plus and minus happen. Okay, anyways, so 72 divided by 9 gives me 8. 8 times 4 gives me 32. So 32 is the answer. Alright, so is there any question except for the silly mistake? Is there any other question? Is it clear? Yes, no? All right, is it clear? Shall we move on to the next problem? H is less than R. Okay, we should use which formula? You mean to say this one? GH equals to G into 1 minus twice H over R. You want to use this formula? So see, this formula is applicable when H is very, very small compared to R. Okay, so by small, what do I mean? 5%, 10% at max. Okay, up to that, this formula will be applicable. But here, H is comparable to R. Okay, the height is equal to R divided by 2. Okay, it's 50%. Okay, half of R is 50%. Formula is applicable up to what? 5%, 10% at max. It will give you some approximately good results. Okay, this is approximate formula. This is an approx formula. So it is applicable only when H is very, very small compared to R. Okay, good. Till what value? 5%, at max 10% or something. Okay, and if options are very far apart, then you can use up to 15% or something, not more than that. Alright, here H is 50% of R. It is half of R. Half of R means 50%. Okay. Alright, so in this case we have to use this formula and not the approximate one. Okay, so let's move on to the next problem. A body weighs 200 Newton on surface of Earth. How much will it weigh halfway down the center of Earth? So this is very, very simple. Again, this problem was also simple, and this is also simple. See, weight is given 200 Newton on Earth's surface. So this is equal to what? mg. And question is, what will be weight halfway down to the center of Earth? So how much is depth? So depth here is equal to r divided by 2. Okay. So we have formula for acceleration due to gravity at depth d. It is equal to what? G times 1 minus d by r. Okay, and d is equal to r divided by 2. So it is g times 1 minus r upon 2 divided by r. So this r gets cancelled out. This r gets cancelled out, and we have g into 1 minus half. So which is half, right? So we get g at depth d equals to g divided by 2, and because it is g divided by 2, so weight will also become what? Half. So w at depth d will be equal to w divided by 2, because it is m into g at depth d, and g at depth d is g by 2. Okay, so weight equals to 100. So this becomes what? Sorry, weight equals to 200, and therefore it becomes 100. Okay, this is very, very simple. All right, these kind of, actually this chapter itself is kind of lottery, and there are very often 1 to 2 questions asked. One question is almost fixed. Okay, and again, if you are lucky, you will get 2 questions from this chapter. So this is simple, but provided you know all the formulae, that's it. Okay. The acceleration due to gravity at height h 1 kilometer above the earth. See, this is that, okay, this is that case when h is very, very small. H is equal to 1 kilometer and r is equal to what? 6,400 kilometers. H is equal to 1 kilometer, right? Which is very, very small compared to r, which is 6,400 kilometers. So here we can use that formula. So height 1 kilometer above the earth is same as at depth d below the earth. Then we have to we have to find depth. How much is depth? Okay. So it's given acceleration due to gravity at height h is equal to acceleration due to gravity at depth d. Okay. We can use this is equal to g into 1 minus twice h divided by r. It's equal to what? It is 1 minus g into 1 minus d upon r, or 1 minus d upon r into g. So g gets cancelled and 1 minus twice h upon r is equal to 1 minus d upon r. That means what? Twice h upon r equals to d upon r, and r also gets cancelled. So d equals to 2 times h is the answer. And that is equal to h is 1 kilometer, so it is 2 kilometers. So option C is the answer. Okay, it is very, very simple. All right. Yes, so let's move on to the next problem. Next problem is starting from center of earth having radius r, variation of g is shown by. Okay, so we have seen this. Okay, I had drawn the graph and I told you the graph is important, memorize it. So option B is the answer. So from center of earth, how does acceleration due to gravity vary with respect to the distance? It varies like this. So it goes on increasing till distance r, then it decreases as 1 by r square. Okay, so this is straightforward, direct question. Okay, from NEET 2016. Simple. Let's see next question. The height at which the weight of body becomes 1/16th its weight on surface of earth. We have to find this height. Okay, so we know, so GH should become what? 1/16th as that of G on earth's surface. Okay, so GH we know it is given by this formula, G upon 1 minus h by r, sorry, 1 plus h by r raised to 2. Okay, in multiplication it is 1 plus h by r raised to minus 2. In denominator it is 1 plus h by r raised to 2. Okay, and it is given that this is 1/16th of G, this thing. So that means now G and G gets cancelled out. So 1 plus h by r raised to 2 is equal to 16. This is what we get. So this gives us 1 plus h by r raised to 2 equals to 16. That means 1 plus h upon r equals to how much? Square root of 16. Okay, we are taking square roots on both sides. So this is 4. So let's take 1 on other side. So it is h upon r gives us 4 minus 1, that's 3. And that means h is equal to how much? It is 3 times r. So 3 times r is the answer. Option C. Very straightforward. Okay. Yes. Is it clear? Okay. Let's move on to the next problem. The next problem is the work done to raise a mass m from the surface of earth to a height h which is equal to radius of earth is. How much will be the work done? So as work is done, as object is raised, there is change in its potential energy. Okay, so what is work done? work done is equal to final potential energy minus the initial potential energy. Okay, so we know the formula for potential energy. So it is equal to what? It is raised from Earth's surface, right? Mass m, it is raised from surface of Earth to height h, which is equal to radius of Earth. So h is equal to r, it's given. So minus of gmm over, we have r plus h, minus potential energy on Earth's surface is minus of gmm divided by r. Okay, so then this minus minus becomes plus, so we have minus of gmm divided by r plus h is 2r, because h is equal to r, right? So plus we have gmm divided by capital R. So it is minus half of gmm upon r plus 1 gmm upon r. So gmm upon r we can take common, it is minus half plus 1, which is half. Okay, so this is equal to half of gmm over r, and as I told, we have to memorize this very crucial trick for this chapter. So what do we have to memorize? gm equals to what? G times r squared. Okay, so if we substitute that over here, what do we get? So we get, it is equal to half of g into r square into small m divided by r, and this r and r gets cancelled. Okay, so one of the r from the square gets cancelled with r in the denominator. So what do we get? It is equal to which option? Half of mgr. Okay, option D is the answer. All right, so work done is change in potential energy, that is final potential energy minus initial potential energy. And what is formula for potential energy? It is minus of gmm, g capital M into small m divided by r plus h. Okay, so this is the final potential energy. Potential energy on Earth's surface is minus of gmm divided by r. Okay, so this minus minus becomes plus, and h is equal to capital R. So it is r plus r, 2r, and then if we add this, we get what? Half of gmm divided by r. And then we use this trick. This trick is very crucial, very important for this chapter. So g into capital M is equal to what? Small g into r square. Okay, so if we substitute that over here, what do we get? We get this thing. So g r square into m upon r, and one of the r's gets cancelled out. So answer is half of mg into r. Okay, option D is the answer. So very simple. All right, provided we know the trick. Okay, so let's move on to the next problem. At what height from the surface of Earth the gravitational potential, it should be gravitational potential and value of g are, this is potential, this is g respectively. Take the radius of Earth as 6,400 kilometers. So let's try to solve this. So gravitational potential is equal to what? It is minus of gmm divided by r plus h. And what is g at height h? This will be gravitational potential at height h. So g at height h is minus of gm over r plus h square. Okay, so can we relate these two? Yes, we can relate these two, right? So we can substitute that this is equal to, I want to divide and multiply with r plus h, or here what I can do is I can write this as minus gm upon r plus h square into r plus h multiplied by m. So I have multiplied and divided by r plus h. Why? Because I have to substitute acceleration due to gravity in this formula. I want to relate acceleration due to gravity and gravitational potential. So what do I get? So I get that this is equal to, so v at height h is equal to minus of, okay, this is also negative, so that minus sign will get cancelled. Minus gm over r square is g at height h. So we have in multiplication r plus h multiplied by mass of the body. Okay. Oh, we want gravitational potential and not energy. So there is no m, no small m in the formula for gravitational potential. So there is no m. Okay, that's my mistake. Sorry for that. It's okay. So we get Vh, the potential at height h, is equal to minus gh into r plus h. The formula that I had written is for potential energy. Okay, and since we're solving similar problems, I wrote the same formula, but here there is no m, right, in formula for gravitational potential. All right, then we get this relation, and then we just have to substitute the values to get the h, but it will be a lengthy calculation, I guess. Let's see. Okay, so it is 5.4 into 10 raised to 7, and this negative sign is also not there because g is equal to what? It is minus gm over r plus h square. Okay, so it is equal to gh. We want h, no? So let's take other things on other side. So h, r plus h, I can say it will be equal to vh over gh, and I want h only, so it is vh over gh minus r, right? Yeah, minus r. Okay, so then h will be equal to, we have to substitute the values. What is vh? It is this thing, 5.4 into 10 raised to 7, 5.4 into 10 raised to 7, and in denominator we have gh, which is 6. Okay, so divided by 6 minus we have r, which is 6,400 kilometers. So 6.4 into 10 raised to 6 we can write. Okay, so this is equal to 5.4 divided by 6 is how much? 6 nines are 54, so this will be 0.9. 0.9 raised to 10 raised to 7 is 9 into 10 raised to 6, minus we have 6.4 into 10 raised to 6. So if we do the subtraction, what do we get? 9 minus 6.4 is how much? It will be 2.6. Okay, so 2.6 into 10 raised to 6, or 2600 kilometers. All right, because 10 raised to 6 can be written as 10 raised to 3 into 10 raised to 3, so it is 2.6 into 10 raised to 3. Okay, this will be 2600, and this is, so this 10 raised to 3 can be written as what? 1 kilometer. Okay, because 1 kilometer is 10 raised to 3 meters. All right, so this is the answer. Option C is the answer. Okay, so this is also another simple problem, but yes, we have to do some calculations over here. Okay, so is it clear? Okay, let's move on to the next problem. Next problem is infinite number of bodies, each of mass 2 kg, are situated on x-axis at distance 1 meter, 2 meter, 4 meter, 8 meter respectively from the origin. So we have infinite number of bodies, many bodies. They are situated on the x-axis at what distances. So this is our origin O at distance 1 meter. Okay, this is 1 meter, 2 meter, 3 meter, so on and so forth. Like this, there are infinite bodies, and their masses are 2 kg each. So 2 kg is the mass of each body. Okay, then question is, the resulting gravitational potential due to this system at the origin will be, how much will be the resulting gravitational potential due to this system? This is the question. So we know what is the formula for gravitational potential. So V is equal to minus of Gm over R, and here we have n bodies, right? Here how actually infinite bodies. Okay, so here there will be gravitational potential due to first body plus second body plus third body plus so on and so forth up to V infinity, infinite body. Okay, that can be written as, what will be distance of all these bodies from the origin. So the distance is, for first body, let's suppose it is R. For second one, it will be what? It will be 2R. Okay, for first body it is R. For second body, this distance will be 2 times of R. For third body, it will be 3 times of R, and so on. Alright, so this can be written as minus Gm over R plus minus Gm. The formula for gravitational potential is minus Gm over R. So here it will be 2R, y minus 2R plus minus Gm divided by 3R, because distances are increasing. Okay, so what can we do here? So what we can do is, we can take minus Gm over R common. So from first term we have 1, from the second term we have half, from third term we have 1 by 3. Okay, and yes, so after that, oh no, it is 1 meter, 2 meter, 4 meter and so on, 4 meter, 8 meter. Okay, so it is not 1 meter, 2 meter, 4 meter, 8 meter, so not 3 meters. So here it will be 1 by 4, the next term will be 1 by 8, so on and so forth. Okay, up to infinity. So this is a geometric series, right? So if we multiply the first term of this series with half, we get next term. Then we multiply that term with half, we get next term. Then we multiply that term with half, we get next term. So what is the ratio of this series? It is 1 by 2. Okay, because if we multiply this, we'll get, if we multiply by half, we get the next term from this series. So it is minus of Gm over R multiplied by, let's suppose A is the first term. Okay, so what is result of the geometric series? What is the sum of geometric series? It is A divided by 1 minus R, right? So where R is the ratio and A is first term of the series. So what is first term? It is 1. Okay, what else is there? And R is equal to what? R is also 1 meter. So yes, let's substitute another page. Let's put another page. So it is minus of, so we are given with M is equal to 2 kg, R is equal to 1 meter. We can substitute that too. So we get V is equal to minus of G into M is 2, R is what? R is 1. So G into 2 divided by 1 multiplied by 1 upon 1 minus half. Okay, so this is geometric series. First term is A, that's equal to 1, and what's the ratio? It is R is equal to half. Okay, then the result will be A divided by 1 minus R. So if we substitute that, what do we get? So we get it is equal to minus of G into 2, and this is 1 minus half in denominator, that is half in denominator, so it will be 2 in numerator. Okay, so minus 4G should be the answer. Alright, so minus 4G is the answer. Let's check. Yeah, so option B is minus 4G, and that is our answer. Okay, so this was somewhat, I guess this was the best question of all. Somewhat mathematics was involved, somewhat thinking was involved. Okay, so this was good question. So minus 4G is the answer for this question. All right, then let's move on to the next question. A body of mass m is taken from Earth's surface to height equal to twice of radius r. Okay, the change in potential energy. This is direct question. So what will be change in potential energy? Potential energy at final point minus potential energy at initial point. So what is potential energy at final point? Gmm divided by r plus h, minus potential energy at initial point is Gmm divided by r, because initially it is on Earth's surface. So potential energy is, so we have this r in denominator. Okay, and how much is h? It is twice of the radius, so we can substitute that. So minus, we have Gmm divided by r plus 2r, and this here there is one negative sign. Okay, because we have to subtract potential energy, and potential energy is minus of Gmm over r. Okay, so this minus minus becomes plus, so we have this thing, and we can take Gmm or r common. So from first term we have minus 1 by 3, because in denominator we have 3r, r plus 2r is 3r, and we have taken r common. And from second term we have 1, so minus 1 by 3 plus 1. How much will be that? So 1 can be written as 3 by 3. So 3 by 3 minus 1 by 3 is 2 by 3. Okay, so this is 2 by 3 Gmm over r. This is the answer, and there is only in one option there is 2 by 3, so D should be the answer, but it is mgr. So as you know the trick now, what is the trick? Gm is equal to gr square. If you substitute that in this formula, you will get what? In place of this Gm, substitute gr square, so 1r will get cancelled, and the answer will be, okay, 2 by 3 g, not g, g into m r, right? Okay, is it clear? Or let's use next page for this. Okay, so what I was saying is, the trick is to use Gm equals to g into r square. Okay, so uf minus ui is equal to what? It is 2 by 3. It is 2 by 3 g capital M into small m over r, and use Gm equals to gr square in this one. So 2 by 3 gr square into m over r, and this r gets cancelled with this one. Okay, so you get this is equal to 2 by 3 g m into r. Okay, gr into m or gm into r, which is this answer. Okay, it's simple. This was straightforward direct question. Okay, final potential energy minus initial potential energy. So provided you know this trick as I told, it is very important, and we have seen this in 2-3 problems based upon gravitation till now. Okay, all right, let's move on to the next problem. So the ratio of escape velocity at Earth to the escape velocity at a planet Vp whose radius and mean density are twice as that of Earth is. This is the question. So escape velocity, what is the formula? Escape velocity is square root of 2 times g into m over r. And what's question? So the escape velocity on Earth to the escape velocity on planet whose radius and mean density are twice. Okay, so radius of the planet equals to twice radius of Earth, and also the mean density of planet is equal to twice density of Earth. Okay, this is given. So escape velocity on Earth, it is given by this formula. Escape velocity for the planet will be equal to what? Square root of 2 times g into mass of planet divided by radius of planet. Okay, so yeah, so we have to solve this. So now we can divide it. So let's divide first equation by second equation. What do we get? So this gives us escape velocity on Earth divided by escape velocity on planet. It is equal to, so 2 and g will get cancelled if we divide these two equations. Okay, so we have m divided by r, and then dividing by this will be equal to multiplying by its reciprocal. So we'll have rp divided by mass of planet. Okay, and then we have to, yes, how much is radius of planet with respect to radius of Earth? It is twice. Okay, it is given, it is twice the radius of Earth. Then we have to substitute for mass of the planet and mass of the Earth. Okay, all right, so let's do that. So we have velocity on Earth divided by velocity on planet, escape velocity. The ratio of that, what we are left with is, it is mass of Earth divided by into 2 divided by mass of planet. Now it's given that the density of planet and radius of planet are twice. So the mass of planet will be how many times? What is mass? Mass is equal to density into volume, right? So it is rho times 4 by 3 pi r cube. Okay, so I want mass of planet, it will be equal to density of planet multiplied by 4 by 3 pi into radius of planet raised to 3, and we know that density of planet, it's given that it is 2 times density of Earth, radius of planet is 2 times radius of Earth, so we can substitute that. So density is twice the density of Earth multiplied by 4 by 3 pi, and this is twice the radius of Earth raised to 3 we have. Okay, so 2 cube is 8, right? This 2 cube is 8, so we have that 8 and this 2, so I can write this as 2 times 8 multiplied by rho into 4 by 3 pi r raised to 3. Okay, and what is 4 by 3 pi r cube? Is it going out? Oh, I'm sorry for this. So okay, so what I was saying is mass of the planet is equal to what? Density multiplied by volume. Okay, so it is density multiplied by 4 by 3 pi r cube. Okay, so density is density of planet, radius will be radius of planet. Then I substituted that density of planet equals to 2 times the density of Earth, and radius of planet is 2 times the radius of Earth, that I substituted. So we have this 2r raised to 3. Okay, so what is 2r raised to 3? It will be 8r cube. So I will take that 8 over here. Okay, so I can write this as this 2 and 8 from here. I will write 2 times 8 multiplied by, we have rho multiplied by 4 by 3 pi r cube. And what is this thing? This is mass of the Earth. Okay, so it is 16 times mass of Earth, and we can substitute it here. Okay, so let's do that. Velocity on Earth divided by velocity on planet equals to square root of m into 2 divided by 16 times m. This is mass of planet, we just calculated this. So this m and m gets cancelled out, and what we are left with is, it is equal to 2 by 16, it's 1 by 8, or you can write it as 1 divided by 4 into 2. Square root of 4, let's check the options. Okay, so square root of 4 is 2, so it will be 1 over 2 root 2, right? So option D is the answer. What is the ratio? 1 is to 2 root 2 is the ratio. Okay, so somewhat lengthy question, but still straightforward. All right. Okay, strangers music. Yeah, thank you. Okay, let's move on to the next problem. A black hole. So this is an interesting problem. A black hole is an object whose gravitational field is so strong that even light cannot escape from it. Okay, even light cannot escape. To what approximate radius would Earth, mass is given, have to be compressed? Okay, what should be radius of Earth to be a black hole? So we are going to compress Earth and we will make black hole out of it. Okay, so this is the question, what should be the radius? So we know escape velocity is equal to square root of 2 times g into m over r. So now we are changing r, so I will write it as r prime, because if I write r, it means it is radius of Earth. We are going to compress it. Okay, so escape velocity. Now light should not escape. That means what should be the escape velocity? It should be equal to velocity of light, which is c. C is equal to 3 into 10 raised to 8 meters per second. Okay, so c equals to this. Escape velocity is equal to c. It is 2 times gm or r prime. So if we square it, we'll get c square equals to 2 times g into m over r prime, and then r prime is equal to 2 times g into m divided by c square. Okay, so let's substitute the values. It is 2, g is, oh, it will be lengthy calculation, 6.67 into 10 raised to minus 11. All right, let's reserve some space for it. So this is equal to 2 into 6.67 into 10 raised to minus 11 divided by what is mass? Mass is 5.98 into 10 raised to 24. So 6 into 10 raised to 24. Okay, 5.98 is close to 6. C square. So C is 3 into 10 raised to 8. Square of that will be 9 into 10 raised to 16. Now, okay, this will be close to what? So this 10 raised to 16 will cancel it out with this thing. So 10 raised to 24 divided by 16, that means 24 minus 16 is how much? 8. Okay, so we have 10 raised to 8 and here it's minus 11, so 10 raised to minus 3. So we'll cancel all this and we'll be left with 10 raised to minus 3 from all that. So we have 6 times 2 into 6.67. Okay, so it is 12 multiplied by 6.67. So it is how much? Close to 12 sevens are. Okay, we just want order of magnitude. So 12 sevens are how much? 84, and 84 raised to minus 3. So 84 I will approximately write, it is nearly equal to 100, right? Okay, 100 and divided by 9. So it will be what? 10, because we just want order of magnitude. So it is 84 upon 9 is, okay, 9, close to 9. So 9 we will approximate by 10, and 10 into 10 raised to minus 3. Okay, so this is the answer. 10 raised to minus 2 is the answer. Thank God that we just need order of magnitude here. So 10 raised to minus 2 is the answer of this question. Okay. Alright, so then let's move on to the next question. The Earth is assumed to be a sphere of radius r. A platform is arranged at height r from the surface of Earth. The escape velocity of body from this platform is f times v. Okay, where v is escape velocity from the surface of Earth. The value of f is, what should be value of f? Alright, so escape velocity from Earth's surface, we know it is square root of 2 times gm divided by r. Escape velocity at height h is equal to 2 times of square root of 2 times gm divided by r plus h. Okay, and it's given that it is equal to some f times escape velocity on Earth. Okay, so this is f times escape velocity on Earth. This is given. We want to find that f, value of f. So it's equal to, here in denominator we have what? R plus h. H is equal to what? What is h in this problem? Height r. Okay, h is equal to r. Let's substitute that. So it is square root of 2 times gm divided by 2r. Okay, which can be written as, it is f times ve. It is equal to, I will take 1 over root 2 common from here, and then again I get 2 times square root of 2 times gm over r. Why did I do this? Because I want, since on left hand side I have f times v, I want on right hand side something times v. Okay, ve, and v equals to square root of 2 gm divided by r. Okay, so this is equal to ve. We can cancel it out. It is escape velocity from Earth's surface. So we get the value of f, which is square root of, 1 over square root of 2. Option C is the answer. Okay, so simple problem, simple, very very simple. Okay, all right, let's move on to the next one. A remote sensing satellite of Earth revolves in circular orbit at a height 0.25 into 10 raised to 6 meters above the surface of Earth. If Earth's radius 6.38 into 10 raised to 6 meter and g equals to 9.8 meter per second square, then the orbital speed of the satellite is. Orbital speed is asked. So what is orbital speed? Formula for the orbital speed or critical speed, it is square root of g into m divided by r plus h. Okay, so it is given in terms of g over here. So it is equal to square root of g, yeah, let's take another formula, second formula. It is square root of gh into r plus h. Okay, let's take this formula. So now we just have to substitute values. It is 9.8. What is value of r? R is 6.4 into 10 raised to 6. 6.4 into 10 raised to 6 plus what is h? H is 0.25 into 10 raised to 6. So 0.25 into 10 raised to 6. So we can take 10 raised to 6 common, and its square root will be 10 raised to 3. So 10 raised to 3 is there, and what are we left with? It is 9.8 plus 6.4, sorry, into 6.4 plus 0.25. Okay, I have taken square root of 10 raised to 6 outside. So what will be this? So 6.4 plus 0.25 will give you 6 point. So this is equal to square root of 9.8 into 6.65. So there is no space over here. Let's shrink it. Okay, so VC equals to square root of 9.8 to 6.65, right, into 10 raised to 3. So this will be close to, I guess, this will be close to 64. Okay, and what is square root of 64? It's 8. Okay, it will be close to that. So 8 into 10 raised to 3 meters per second. So the answer is closest to 8 is 7.76. So option C should be the answer. Okay, so we cannot do all the calculations. So closest answer will be 7.76 kilometers per second. All right. So yes, this was very simple. Let's move on to next one. A satellite S is moving in elliptical orbit around the Earth. Mass of satellite is very small compared to mass of the Earth. Then the linear momentum S remains constant in the magnitude. Okay, this is actually linear momentum. It will change because it is moving in elliptical orbit. All right. So as it moves away from Earth, its velocity will decrease. As it moves closer to Earth, its velocity will increase. So momentum will change. Momentum is mass times velocity. As distance changes, momentum changes. Okay, so linear momentum changes. The acceleration S is always directed towards the center of Earth. Yeah, so when satellite moves around Earth in circular orbit, there is centripetal acceleration acting on it, which is directed along the radius and towards the center of Earth. So this answer is correct. Option B is correct. Okay, so we need not even look at the other options. All right, let's move on to next one. A geostationary satellite is orbiting Earth at height of 5r above the surface of Earth, r being the radius of Earth. The time period of another satellite, there is another satellite of at height 2r from surface of Earth is. Okay, so what will be T1 by T2? We know that T square is proportional to r raised to 3. So T1 by T2 square will be r1 by r2 cube. Okay, and first one is geostationary satellite. That means its time period is 24 hours. Okay, so r1 by r2. R1 is what? Its height is 5r. So it is r plus h. Okay, is what we are writing. R1 equals to r plus 5r. R2 is r plus 2r. Okay, this is the total distance. That means it is radius of Earth plus height of the satellite. Okay, so it is r plus 5r in first case, r plus 2r in second case, and we have this raised to 3. Oh, so this is 24 hours divided by T2, and we want T2. So here it will be 5r plus r is 6r, and in denominator we have 3r. So 24 hours divided by T2 equals to 6 upon 3. We have square of this is cube of this. So 2 raised to 3. Okay, because 6 by 3 is 2. 2 raised to 3 is 8. Okay, and this is equal to 24 hours upon T2. So what will be T2? T2 is equal, square of that. Okay, so we have to take square root of this. So T2 will be what? It will be, let's take T2 on other side. Let's take square root of 8 first. So 8 raised to half is what? 24 divided by T2. Okay, and if I take that T2 on this side, so that 8 will go into denominator. Okay, so let's do that. So in this step itself, I will write it is 8 raised to half. So this 8 raised to half I will take in denominator, and T2 I will take on other side. So T2 equals to 24 divided by 8 raised to half, or square root of 8. So how much is that? 8 you can write as 4 times 2. Okay, so 4 times 2, square root of 4 is equal to what? It is 2. So 24 upon 2 root 2 you have. So 24 upon 2, right? 24 divided by 2 is what? 12. 12 divided by root 2 is the answer, or 6 root 2. Okay, 12 divided by root 2 can be written as 6 into 2 upon root 2, and this 2 upon root 2 gives root 2. So 6 root 2 is the answer. Okay, so yes, this is direct question again. T square is directly proportional to R cube. If we know this, we can solve this. Okay, simple problem. Alright, let's move on to the next question. The radii of circular orbits of satellites A and B of Earth are 4r and r respectively. If the speed of satellite A is 3v, then the speed of satellite B will be. So this is again straightforward question. For satellite 1, what we can write? So v1 equals to square root of gm over r1. v2 will be equal to square root of gm over r2. Speed of first is given, it is 3v. So if we divide this, what do we get? So v1, or let's take v2 upon v1, it will be equal to square root of gm over r2, and dividing by this is multiplied by its reciprocal. So multiplied by, we have r1 over gm. So gm gets cancelled. So, and v1 is 3 times v, we can write it. So v2 upon 3 times v is equal to, what is value of r1 and r2? r1 is 4r and r2 is r. So let's substitute that. This is 4r, this is r. Okay, and r also gets cancelled. So square root of 4 is 2. Let's take 3v on other side. So v2 equals to 2 times 3v, so 6v. So this is the answer. Okay, so option B is the answer. Alright, so yes, this is how we solve problems based upon gravitation. Okay, so you have seen many problems, solution of many problems. You have seen me solving many problems. Now it's your turn to solve problems. Please try many questions on gravitation. Please, if you like, you can check the theory again, or if you like, you can watch the lecture again. Okay, where we have covered theory in short, and please try some problems. Okay, you will be able to solve. All right, so this is all for today's lecture. Let's end it here. So tomorrow we'll start with rotational motion. Okay, bye.